Welcome, everyone. My name is Andrew. I am the Director of Strategic Alliances and Business Development here at Newton AI. Today, we are going to share with you a presentation of how to bring AI to edge devices in just a few steps. I'm super excited today. We have Gianmarco, who's the team lead of the ML group at ARM, and also the author of the TinyML Cookbook. And so welcome, Gianmarco. He has been part of a team and tech lead in the machine learning group at ARM, who co-created the ARM Compute Library in 2017. And the ARM Compute Library is currently the most performant library for ML in ARM and is deployed on millions of devices worldwide, from servers to smartphones. So welcome, Gianmarco. We're super excited to have you.
Thanks a lot for this introduction. I'm honestly super happy to be here, Andrew, really.
Awesome, awesome. Yeah, and so your book was just released on April 1st, which is awesome, so it's available. And today we're going to have an overview of the TinyML Cookbook and a practical use case. And then we're going to look at how we can leverage the Newton TinyML platform in order to build this model in just 3 clicks. So Gianmarco, if you want to go ahead and take it over, and then we can get started.
Absolutely, and thanks a lot again, Andrew. So let me share my screen. Okay, I believe you can see my screen. Can you see my screen, right?
Yes, we can. Perfect.
Okay, so let me start from the agenda of my part. As Andrew said, in this presentation, we have split this presentation in 2 parts, mainly the part where I'm going to talk about a bit the TinyML Cookbook, but just a bit, and more about a practical exercise with TinyML. In the second part, actually, Andrew is going to talk about the same use case by using the Newton AI. And the use case we have, we are going to present today is about forecasting snow. It's a very simple, I would say this is a hello world use case for TinyML, but it's going to be important for understand all the necessary steps for developing a TinyML application, and also see how these steps can be also make it simpler with the help of Newton AI. So this is the agenda for my part. So in the first part, I'm going to talk about the motivation about the book and its target audience, a bit about the book structure, in the core part of this of my presentation is going to be about the forecasting snow with TinyML. So let's talk about TinyML in general, because probably you are aware of what an ML is, but if you are not aware of TinyML is, here there is the definition of these of TinyML. So this is more or less the definition you can find on the internet. This TinyML is a fast-growing field at the intersection of machine learning, embedded systems, in order to enable smart applications on low-power devices. So the 3 keywords for TinyML are definitely machine learning, embedded systems, and low power. In the context of the book are deep learning for machine learning, microcontroller for embedded devices, and milliwatt in terms of when we refer to power consumption. Milliwatt because we are going to use microcontrollers. We usually have this power consumption range. So these are the 3 ingredients, but the main important aspect to consider is the word underline, intersection. This is a field that needs to know where machine learning and a target platform need to know each other best, because we cannot deploy any application if machine learning or the machine learning model does not know the target platform. This is completely different from what we have seen in the past of smartphone, for instance. Here is not just a matter of make it faster. Here is a matter to make it working, because the devices we are going to work on have just few kilobytes of RAM and probably a few megabytes of program memory, which is really similar to the hard drive we have on a desktop. So what is the motivation about the book? So the motivation is this. So with TinyML Cookbook, I like to demonstrate how easy is TinyML for everyone, even for those with no or little familiarity with embedded programming. Why this motivation? Because the first time I heard about TinyML was in 2013. So definitely not years ago. I mean, in 2013, we were already talking about machine learning microcontrollers, but it wasn't TinyML, because machine learning, it was more complicated than now. It wasn't that easy. You had to be an expert in order to be to deploy a machine learning model. But also you had to be an expert or embedded programming expert to program microcontroller. I still remember that in some cases I had to use assembly, and most of the time the code I was writing for a microcontroller couldn't run on another microcontroller. Now it's completely different. You don't have to be a machine learning expert. And this is demonstrated also by end-to-end tools like Newton AI, for instance, that can make machine learning easy for everyone. But also on embedded programming side, is extremely easy to program microcontrollers, because as shown in the TinyML Cookbook, now there are IDEs which are in the web browser. You just need to open a web browser, connect your microcontroller, and you can easily program your boards. So it's extremely easy, and we're gonna see this today. So the target audience, so probably you can understand more or less what the target audience is. So the in particular machine learning developers interested in developing machine learning applications, so smart applications through machine learning on microcontrollers, but through practical examples. This is not just a theoretical book. This is a book where you're gonna learn doing something. You're gonna do projects. You're gonna experiment with sensors. You're gonna experiment with different use cases, which are different in terms of difficulties and so on. However, if you're not a machine learning developer, but you have a bit of knowledge of machine learning, so you are an embedded developer with a bit of knowledge of machine learning, this can be a helpful book also for you, because you can benefit from extending your knowledge and learning more about the current tools we have in the TinyML ecosystem. So in terms of book structure, so the book has different projects, but the book wants to show different development scenarios. So the idea I had was to use two different microcontrollers for different development scenarios. And the boards using the book are the Arduino Nano 33BLE Sense board and the Raspberry Pi Pico. What development scenarios will be shown in the book? A scenario where you have a board with all the sensors and you don't have to connect anything to that. So you have a board with a microcontroller and the sensors on board. This is going to make TinyML extremely easy, because you have everything there. And most of the time, you don't need to expand the board with extra sensors. On the other side, we have Raspberry Pi Pico, which is a powerful platform, but it has just a microcontroller. So in this scenario, you need to learn how to connect sensors to the board, how to build simple electronic circuits, to experiment with TinyML. That is the reason I've chosen these two platforms. However, there are also two chapters. Well, the reader will use virtual platforms to experiment also with other scenarios where you probably want to experiment TinyML, but you don't want or you don't have the platform to play with. In terms of software tools, so I can definitely say that TinyML Cookbook is a snapshot of the present software tools. Why I'm stressing this aspect, it's pretty simple. TinyML is under heavy development. There are different tools evolving. And what is presented in the book is actually what we have right now. But I'm pretty sure we'll have something new in the near future. And these softwares will cover both the machine learning development and embedded programming. For example, you use TensorFlow, or you use Arduino IDE for programming the boards, both the Raspberry Pi Pico and the Arduino Nano. However, thanks to Arduino, Edge Impulse, and Google, these tools will be cloud-based or actually browser-based and with a free plan for our usage. So it means you will not need to install anything apart from the subscription. So less hassle to step up your TinyML applications. So you will focus directly to the applications rather than installing all the dependencies to play with the tools, which is definitely desirable. In terms of where to learn more about the book and the projects, you can definitely refer to GitHub, where the source code is hosted there under MIT license. So definitely you can copy and paste and integrate in your projects if you want. But also the learning doesn't stop there on the book. The learning continues on Discord. We have a community there where we try to engage with the readers to learn more from them, from their use cases. And also I really hope to help them to enter the TinyML world as well. So in terms of what you will learn, quickly, these are the main things you are going to learn with TinyML Cookbook. So definitely the relevant microcontroller programming fundamentals for TinyML. As I said, TinyML is not just machine learning, it's also embedded programming. So this book will teach you also how to build basic electronic circuits for TinyML. You will play with different sensors like microphone, camera, and accelerometer. You will definitely learn how to run machine learning on microcontrollers. This is a topic of the book. You will implement an application that responds to human voice, for instance. In this case, you will build an application to recognize 6 different words, 1, 2, 3, and red, green, and blue, for instance. You will apply transfer learning to classify indoor environments. And in this scenario, we'll also learn how to implement an efficient pipeline to transform the camera frame to the expected input of the model. That is an important use case for TinyML because, well, most of the time we think, oh, we have a machine learning model, but most of the time the sensor does not provide the input that the model wants. So in this scenario, you will learn how to build an efficient, in terms of memory utilization, pipeline to transform the camera frame to the expected input for the model. You will design a CIFAR10 model for a microcontroller with just 64 kilobytes of RAM. And this chapter is, in short, the chapter where you will learn some good practices to build tiny machine learning models for microcontrollers. And in the end, the book will end with an implementation of image classifier on a virtual ARM Ethos U55, which is a micro MPU attached to the microcontroller, which promises to unlock other use cases for TinyML. So it definitely improves the performance, but also the power efficiency of our devices. But today is not just about TinyML Cookbook. Today we're going to talk about how to focus the snow with TinyML. We like to explain what are these steps to implement a TinyML application. And so if you're not familiar with TinyML yet, or you have just started, this could be an interesting session to understand what steps are involved for building a TinyML application. But before showing the steps, let's present the problem, or actually where this problem is presented in the book. This project is presented in the chapter 3, which is the first chapter about actually a TinyML project in full, and it presents all the development steps of a TensorFlow-like micro-based application for microcontrollers. So when you read the book, the 3rd chapter is actually the chapter where you're gonna see TinyML in action, which means both machine learning and embedded together. Chapter 1 is mainly about TinyML in general, from a theoretical point of view. But the 2nd chapter is mainly about just embedded programming. The 3rd is TinyML. So what is the goal of this chapter? Well, It's pretty simple. We want to focus the snow. And to do that, we want to use the temperature and humidity of the last 3 hours. So as shown here in this slide, we have T0, T1, and T2, H0, H1, and H2, which are the temperature and humidity of the last 3 hours. The machine learning model will take these and will predict the snow. I mean, if it's gonna snow or not. What you will learn with this practical exercise, you will learn all the development stages of a TensorFlow-based application, as mentioned before, but also you'll learn in this chapter how to acquire temperature and humidity sensor data. And when I say this, since we will use 2 different platforms, like Raspberry Pi Pico and Arduino Nano, it means that on Arduino Nano, you will use the onboard sensor for the temperature and humidity data. For Raspberry Pi Pico, you will use an external sensor, which is a DHT22, to get the temperature and humidity data. What you will do, you will collect historical weather data and build a balanced data set. You will design and train a machine learning model. You will build an electronic circuit with this external sensor with Raspberry Pi Pico, because it doesn't have an onboard sensor. And you will deploy the model on the platform on both Arduino Nano and Raspberry Pi Pico. For today, we will mainly focus on the machine learning development, because I cannot show in the application up and running, because I'm on the laptop that does not support the connection with the Arduino Nano, but we'll see all the tools in actions anyway. In terms of what you're gonna do, we're gonna do this workflow. So, but please don't focus now on this. We're gonna see all the steps in a bit, step by step. How many steps? We should have just 6 steps to implement this project. So for forecasting snow. So let's start from the first one. And probably I like to use the slides, but also jump to the Colab in order to show the code in action as well. So step number 1. So the step number 1 is data acquisition. Andrew, can you still see my slide, right?
Yes, I can see your slide. Yep.
That's perfect. Okay. So step number 1, data acquisition. This is your first step in all TinyML applications, but I would say in all machine learning applications. So this step does not change. So we need to focus the snow. So we need to find a resource to download the data set. And trust me, although this is, well, we have the weather data in different resources, trust me, it's not that easy, especially for a commercial book. So, and World Weather Online is an interesting resource for downloading historical weather data for different worldwide locations. Definitely, since we want to focus the snow, we need to be smarter. We need to find a place where it snows regularly. So for example, in the book, I suggested 𝘕𝘂 in Italy, which is a place which usually snows between November and April. So at least a place where I know it snows. So this is the only thing it is required. In terms of what to do, well, it's going to take a few minutes, but okay, here, this is the Colab project that you're gonna develop in the book. This file is actually located in the GitHub repository of the TinyML Cookbook. As I said, it's chapter number 3. Let me also go to the book. Let me see if I can go straight to the chapter number 3 quickly. Yes. This is the chapter number 3, building a weather station with TensorFlow Lite for microcontrollers. At the end of the introduction of chapter number 3, you can click on the link and you go straight to the chapter 3 folder. Inside chapter 3 folder, you have the Colab file that we can import in Colab. So the first step is about generating the data set. Since it takes a few minutes, I'm going to skip it, but I'm going to just comment the code, which is basically straightforward. Nothing really complicated here. We just need to import some Python libraries required for our project, nothing more than that. We will need to install 𝘬𝘀𝑜𝑖𝑠, which will help us to fetch the data from World Online. So we will not share the file with the historical weather data because from the terms of use, you have to subscribe to the World Weather Online. But it's, as I said, it's free for 30 it's free for 30 days, and you can download it. And it's straightforward. It's just a couple of quick clicks, nothing more than that. Once you have installed it, you just need to import the historical weather data with two functions, nothing really complicated. So here there is the location that I put, but if you want, you can put more than one location. You can put, for instance, 𝘘𝘪𝑗𝑧, you can put other places to make your model even more robust. And once you have fetched the data, you need to define a temporal interval. So in this case, I chose 10 years of weather data. Okay, I'm just showing the log because, as I said, it takes some minutes to do it. But once you have collected the data, what you're gonna have a CSV file with how hourly data for that location. What does it mean? It means that for each hour you will know the temperature, humidity, rainfall, snowfall, the wind, and other weather information. But of course, we're not interested in all of them. So we will fetch the data that we are just interested, which are the temperature and humidity and the snowfall. We'd like to know if it snows or not. What is the next step? So the next step is the dataset preparation. So you have the data, but definitely you want a dataset for training your model, which means you need to prepare the training and validation dataset. In this step, we will need to extract the temperature, humidity, and snowfall data that we have just seen in step number 1, actually. We will need to balance the dataset. Why is this needed? Well, as I said, in 𝘘𝘪𝑗𝑧, it typically snows between November and April. So definitely we expect a dataset with more samples where it does not snow than it snows. And this could be a problem when training a machine learning model. And to explain this, let's use a very simple example. Let's assume we have a data set with 99% of the samples where they're saying, well, it does not snow. And 1% that says, well, it snows. Well, the machine learning model can, after training, can basically not generalize properly, which means that actually could fail all the positive samples and returns a very high accuracy. But actually the model does not work fine. So that is the reason we need to balance the data set in order to train the machine learning model properly. Once we have balanced the data set, we will need to scale the input features. Why is this needed? Well, the input features will have a different scale because the temperature can be negative, for instance, and with different range. The humidity is just between 0 and 100. So definitely they have a different range. And if we want, once again, to train the model properly and to converge to a good solution, we need to scale and bring both features to a common scale. Once we have done both, which are the two key in steps in the dataset preparation, we have the dataset ready for training our model. And going back to the dataset preparation, so here there is an extra step which ensures which actually plots the for which temperature and humidity you have this node. And if you pay attention, there are also cases where it returns this node when the temperature is greater than 0. So you may ask, well, why it's possible? Why it's nodes for temperature greater than 0? Because I mean, you typically know that it's nodes for temperature below 0. But this is a case because the temperature reported is actually the ground temperature, but in the air the temperature can be lower than the ground temperature, and that means that actually the snow that reach the ground will probably melt. So actually all of these will probably not be a real snow, let's say. So we're going to ignore for a moment these cases and consider just the snow for temperature which are below, let's say, 2 degrees, just for simplicity. We're talking about a machine learning model where it's gonna say yes, it knows, no, it doesn't know. So which means this is a binary classification. And since this is a binary classification, we need to be careful also on the activation we have on the last layer of our model, which is which is a sigmoid for this specific case. These function, in short, assign yes and no label to the dataset because because the snowfall is not a yes or no, but is actually the snowfall in centimeter. But our problem is mainly about classifying the if it snows or not. So we need to define a threshold to say, yeah, if we have a snowfall above that value, we will consider the snow. Otherwise, no. So this function just do the label, little labeling for the output. And after that, we build the data set. And when I say build the data set, it means that remember that we like to use the last three, the temperature humidity of the last 3 hours. And so we're going to build a data set to contain the temperature at different hour. Andrew, I'm seeing one question in the Q&A session. I don't know if you want to see it now or you prefer me to go ahead.
I think you might want to answer it because it's related to the process. So what is the criteria to decide threshold?
Okay, so the threshold, for the criteria in this case, I use Wikipedia because Wikipedia for the snowfall has a classification in terms of low, moderate, and high. So if the snowfall is greater than 0.2 centimeter, it considered the snow, for instance. We can consider the snow. Otherwise, if it is below, we can, let's say, ignore it for a moment. So in the book in particular, we consider the classification used in the Wikipedia, if I recall correctly. Okay, but of course, these threshold can be also chosen by you. You may have use cases where you probably don't want just to detect the snow, but you want to detect the snowfall directly. And so actually, if this is your use case, you don't need any threshold. So you basically have a different problem. And this could be an interesting case as well. So instead of trying to detect the snow, trying to predict the snowfall instead. That would be a good extension of the project, I believe. Once we have prepared the data set, well, we know that the data set is not balanced. It's not balanced because in the location, it snows regularly, but not the whole year. So we will need to make the data set balanced. What is the easiest way to do it? Well, simply removing the samples with the samples in the no snow class. Because as you can see here, 80% of the samples are assigned to the no snow class, and just 12.89 samples are assigned to the snow class. Since we have enough instances in this data set, it is safe to basically discard some samples from the 𝘲𝑧 class in order to get a 50-50 split. And in the end, the last step is the normalization. The normalization adopted in this case is the z-score. As I said, this is needed to bring both features to the common range. And so in this part of the exercise, you will normalize the data, or you will scale the data in order to have a common range between them. And remember, once you have normalized your data, please take note of these values, because this will be needed also during inference, because you will need to normalize the scale, actually the input of the temperature, humidity, using these values that have been used for training the model.
Gianmarco, we have one question. Where can I find this chapter 3 doesn't seem to exist in GitHub? Maybe you can share the link.
Absolutely. Absolutely. So chapter 3, okay. If I'm talking about just the collab file, let me, I'm going to put in the chat so everyone can use it.
Great. Thank you so much. And please go on. Thank you.
Thanks a lot. Okay. And so after the normalization, there is a simple function to plot, the distribution of the values. And so from the distribution of the values, you can definitely see that before the temperature, humidity had a different ranges. Temperature was negative as well. The humidity was between 0 and 100. After normalization, you can see that the distribution is zero-centered, because the z-score is actually centering the distribution between 0, and the distribution range is actually really similar, is between -2 and 2 for both of them. Okay, so next step is step number 3. We have the training validation data set. The next step is we want to design the model and we want to train it. So what you're going to do in this step, for this specific case, and for in this specific project, the model is really tiny. We don't have to build a big model for forecasting the snow. And this is the model developed in the project for forecasting the snow. You have an input. We have chosen 12 neurons for the first fully connected layer. We use a drop layer, and after that, we use another fully connected with a single neuron. Single neuron because we have a binary classification. Remember, since we have a binary classification, we need at least a sigmoid to have the probability to have one of the two classes, which is it snows or it does not snow. Step number 3, let me go to the, is in step number 3, I combine actually 2 steps, which is a training and design. But in the training, for training the model, we use TensorFlow in the book. So we take the data set, we encode the labels to numerical values, because before we assign the label yes and no, for say yes is knows or no it doesn't, but are not suitable for training. So we need to assign numbers like 0 and 1. And in this case, we use scikit-learn to assign the numerical values, which is definitely straightforward. After that, well, we have the data set. We need to train. For training, we need at least 2 data sets, which are the training and validation data set. The training is used for updating the weights. The validation data set is used during training, remember, during training, to understand how well the model behaves on data not used for training. However, although the validation data set is used for, let's say, evaluating the performance during training, you may consider, well, let me tune some parameters during training. So this means that actually the validation data set could be influenced by you and you, let's say, voluntarily or not, influence the accuracy on the validation data set. For this reason, it's always recommended to have a third data set, which is the testing data set, which is tested after training in order to have an unbiased evaluation of the model. So these are usually the three data sets used for training these machine learning model. We use the Keras API. As I said, the model is straightforward. It's really simple, but this is a hello world example. So we don't want to build a massive or very big model. We just need something simple and make it working. And when you look at TinyML, well, look at the total parameters. These are really important because, as mentioned also in the book, the total parameters will give you an indication on how big the model is and how much memory will be required by your model in the program memory. If we consider microcontrollers, in short, the microcontroller is a tiny computer with a hard drive and a RAM. The hard drive for the microcontroller is called program memory and is usually around megabytes. And in the program memory, you put your model. The SRAM is actually used for the computation of your machine learning model during inference, for storing the temporary buffers or tensors. But these 97 parameters will affect mainly the program memory utilization. So keep an eye also on this number. In this case, it's definitely small, so it's not going to be problematic to deploy on both Arduino Nano or Raspberry Pi Pico. We need to compile the model after that. Binary cross entropy is required because we have a binary classification. Once we have defined or compiled the model, we will need to feed, so we need to train the model. And we just need a few epochs to train this tiny model to avoid overfitting the model, as also shown in with these functions by plotting the accuracy among the different epochs. As you can see here, well, already after 10 epochs, probably the model already reaches its best. So to avoid overfitting, probably it's better to stop at 10 epochs and take the model, and in order to have a more generic solution anyway. And after that, well, we just need to save the model, and that's it. This part is completed. So step number 3 is completed. Okay. Step number 4, we have the model, but there is something not really reported here in the workflow, which is the model testing. Sorry. We have the model, we want to evaluate how good the model is, but not just in terms of accuracy. The accuracy tells us, well, how good the model is to predict the various samples. Perfect. But sometimes it's not good enough, especially if you have an unbalanced data set. It's not our case, but if you have an unbalanced data set, well, the accuracy definitely is not good enough. For having a better understanding of how the model behaves, well, in the book, we evaluate the accuracy or the performance of the model through the confusion metrics and other metrics, which will be shown in a bit in the next window. So as shown in this tab, so we're going to evaluate the model effectiveness through the confusion metrics. You will get a matrix where each block represent. So where, for instance, this block is actually the false, the true negative and true positive. What with true negative means the samples which are correctly classified as no. In this case, we have a true positive samples. So this number of samples which are actually classified correctly and belong to the no class. In the other diagonal, you have samples which are not correctly classified. What can we learn from these confusion metrics? Well, most of the samples are correctly classified, so which is good. So the model behaves in a way in what we want to perform. So we want to classify we want to detect the snow. Yes, the model works. However, we should expect some false detection of the snow, because this is actually the box where we report the samples which are classified as it snows, but actually it does not snow. So we should have more false positive in our example. And as I mentioned earlier, confusion metrics is not everything. There are also other metrics, other performance metrics. And in the book have been reported recall, precision, and F-score. And these have been evaluated to have a better understanding. So the accuracy is around 86%. What is important to highlight, and which is also demonstrated by the confusion metrics, is the fact that the model correctly classified, it's a good model to detect the snow, but we should expect some false detection. So in particular, when the temperature is low and the humidity is really high. So as also demonstrated by the performance matrices reported here. In the book, of course, there are more details about this, and also more details about each performance metrics reported in this project. What is the next step? Step number 5. We are reaching the end of our project. The step number 5 is the model quantization. We have a TensorFlow model, which is definitely perfect for if we want to resume a training, or we want to share our results with our machine learning researcher or scientist. However, for model deployment, this is not a good model, because the TensorFlow model contains information which are definitely not required for just the inference. We want a model that contains just the necessary information for performing the model inference, as I said. But when talking about microcontrollers, well, it's not just a model inference. We need to have a model inference suitable for microcontrollers. Floating point acceleration of microcontrollers, well, it's something you may have, but most of the time you don't have it. With this, I mean that probably the floating point acceleration is available in software, but you don't have the hardware acceleration for it. Why this? Well, remember, one of the goals of microcontroller is to be low power. And in order to be low power, you need to sacrifice some hardware capabilities or computational capabilities. And so for this reason, microcontrollers usually have just integer arithmetics on board. And like the int8 arithmetic. So one of the reasons we do the quantization is this: we want to make the model tiny and also exploit in the most efficient way the hardware computational capabilities of our device. There is another aspect. So before I move on, the quantization is performed using the TensorFlow Lite converter. The TensorFlow Lite converter generates another file, which is the .tflite file. However, for microcontrollers, is not a suitable format. Microcontrollers could not have an operating system, first of all, which means you don't have APIs for reading files from SD card, just to give an example. But one of the reasons I like to say this is not suitable is not this, is actually another aspect. The model is actually constant, and we want to put it in the program memory. However, if you use a file, you don't have the chance to put in the program memory, because the program memory on a microcontroller is a constant memory. Therefore, you need to convert the TensorFlow Lite model or file to something which is constant and can be compiled with the program. In this way, you have your model directly stored in the program memory, which is the hard drive of your microcontrollers. What is the easiest way? Well, simply converting a TF-Lite file to a C byte array, to an array of integers. Are there any questions, Andrew?
The only question that came up was if there was a discount or coupon or special access for the seminar attendees for the book. I know last time we did a giveaway. And then the second one is if we'll be able to share a copy of the presentation. I know the presentation will be available on the YouTube stream as well. And then Yulia had provided our Slack channel in order for people to reach out to us with questions. And yeah, we can also share the presentation in Slack too.
That's perfect. Thanks a lot.
Yep. Okay, hold on. There's actually one more in the Q&A.
Yeah.
So which metric is more important here, precision or recall?
Okay, so let me go to the, well, the precision is actually more important because it I mean, the recall says, well, definitely the model will classify it as no, but it takes in consideration also the fact that you classify there's no also when there's no doesn't happen. So the precision is more important because it also tells us the misclassification and in short tells us how good the model is actually to predict there's no. Of course, it depends also on a use case. In this case, probably I prefer to say, well, it's no's or to have false positive, more false positive than the false negative. Because probably if you want to forecast extreme weather conditions, well, you probably want something that, well, I accept, let's say, to have false positive in my application. In other cases, might be not desirable. In this specific case, probably it's good enough. So it's something that I accept. I accept to have false positive. What I want is to have a model which is capable to tell me that it knows with high confidence, sorry.
Perfect, thank you.
Okay, thanks, Andrew. So step number 5, what to do then? So we have the TensorFlow model. We use TensorFlow-like converter. We will convert the TensorFlow file to TensorFlow Lite, and we will convert the TensorFlow Lite file to C byte array. Remember, this is a crucial aspect, crucial step, because without this step, you will not be able to deploy anything on your microcontrollers. How is this done? So the quantization is actually a simple steps in TensorFlow Lite. So how does it work? So in TensorFlow Lite, you just need to provide to the TensorFlow Lite converter a subset of the data set. Why do we need to provide this subset? Well, the quantization uses some offset and scale for your integer value. Remember that you transform floating point values to integer values, so we are gonna lose some accuracy there. But if you know more or less the range of your samples or the values, you can predict or you can compensate this degradation by estimating correctly the values required for the quantization, especially the offset and the scale. So this is the most important aspect. So given the data set, we provide a subset of this, usually 100 of samples are enough, to estimate the quantization parameters that will allow a good, let's say, estimation of the quantization parameters. Once we have done this aspect, we can proceed with the conversion. And in this case, what I like to highlight are, in short, we are asking a TensorFlow Lite converter to convert all the operations to int8, so to use the operations in full integer 8, and also to convert the input and output to int8. This is actually something optional because you may For example, if you need to anyway to convert the output to floating point, for instance, for knowing the probability, you may consider to ignore this and just output the floating point, so that in short, the model can output directly the floating point value. And the same for the input. In this specific case, we will provide the input and output in int8. So when we will prepare the input data, we would need to be careful on providing the correct quantized values. And once we have done the TensorFlow-like, the conversion to TensorFlow with a TensorFlow-like converter, we can save the TensorFlow-like file. And once we have the TensorFlow, which is here, by the way, and once we have the TensorFlow-like file with a simple program, which is XXD, we can produce the TF-like file as a sequence of hexadecimal number, which can be exported as a const integer array that we can export in our Arduino project, for instance. This is the output generated by the XXD program. I like just to highlight one thing. It outputs an unsigned char. In this case, usually the compiler is smart enough to say, well, this is an array that does not change over time, which means it's a constant value. And if it is constant, I can put it in program memory. However, to be safe, I always recommend to put a const here to be sure that compilers will treat this array as const and then put it in the program memory after that. Any questions?
Yeah, we had two. So does the input size depend on the resolution of the controller's ADC?
Okay, in this specific case, the input size depends on the number of samples. So the input size, if I understand correctly, is the number of elements required by the model to predict the snow, which in this case is 6. Since we're talking about a quantized model, we are talking about 6 bytes, so 6 integer 8 elements.
And then the next question was, how much precision is lost in quantization to integers?
Okay. We could have a dedicated book on this question, actually. But for machine learning is a different story. Well, I like this question, and I can say, well, definitely you lose accuracy also in floating point if you think about it. If you have a floating point and you perform the same operation, changing the order of operations, well, it's not like on paper. In hardware, you have a different result, also in floating point. Well, in integer, definitely you have a drop of accuracy, right? But the machine learning model most of the time is robust enough to avoid this loss precision. So although you have a different, let's say a loss in the arithmetic calculations, at the end, with this quantization and with the correct estimation of the quantization parameters, most of the time, but please, there are also use cases which is not true, you don't lose the accuracy that you have on floating point. But there are some use cases where this could be not true. But in this particular case, it's not a problem.
Great, thank you.
Okay. Okay. Yes, this is the array, and that's it for the machine learning part. So for the machine learning part, we just need to copy and paste this array and to put it in the Arduino Nano. So we can proceed to the last step of this exercise, which is step number 6. Step number 6 is the application development and is about the development of this application for Arduino Nano and Raspberry Pi Pico. As I said, I don't have the board with me, but I will show the steps required for making the application for our microcontrollers. From Colab, So as I said, we just need to copy and paste this array. We just need to go to the Arduino web editor, and we need to import, here is already imported, the file in a model.h file. Here, as you can see, I put a const in front of the unsigned char to remind the compiler, well, this is a constant array, and I want to put it in the program memory, not in a data memory. I'm stressing this aspect because program memory is a constant memory, is usually bigger than a data memory. And so since we want an application to be memory efficient, is more desirable to put in program memory. And we have the model. We just need to include the model. It's just an array, nothing more than that. We need to include all the TensorFlow Lite header files for our application. I'm not going to talk about all of these. In the book, of course, you will have the explanation and the meaning of each header file. What is important for this presentation is actually the concept. So what is needed to make it running? So you definitely need the header files. You need the standard deviation and the mean value that we calculated for normalizing the temperature and humidity when we prepare the data set. So this is something you need to import as well. You will need an array to build a circular buffer. And to explain this, let me go to the slide here. So in particular, slide number, this slide. So we need a circular array because we want to store these values in temporal order. So we have an array with 3 elements for the temperature. We have another array for the humidity. In this array, we will keep the elements in a circular way. So in order to keep it in a temporal order and avoid to do recalculation of the date of the temperature and humidity data. Once we have done, yes, we have a bunch of variables to allocate, but don't pay attention to these. These everything's explained in the book. What is actually important is about the initialization. So in order to make it running or to do the model inference, you just need to load the model that we put in the model.h file. So we get the model. Once we have the model, we need to allocate the operations. We need to initialize the interpreter. The interpreter, in short, will take the model and build a graph with all the operations to execute the model, so which will be fully connected, just fully connected layers plus the sigmoid. Once we have built the execution graph, we'll need to allocate the tensors. What tensors? Are the intermediate tensors required for the computation? And this will be done with this. With this function, we'll also allocate the input and output tensors that you will need to use for feeding the input and also reading the output after the model inference. There are the functions for the quantization and dequantization. These are very simple formulas to perform the quantization and dequantization that you need to apply for feeding the correct input to the model and to read the output from the model. And to do so, you will need to extract the quantization parameter I mentioned earlier when I talk about the data set, the subset of data set that we provide for converting the TensorFlow model to TensorFlow Lite. Once you have this information, you definitely have the quantization parameters, which are the scale and offset, and you have everything for quantizing your temperature and humidity. So, and in terms of application, well, it's really simple because it's a single line in the loop function. Once we have, although it's pretty long, trust me, the execution of the model is a single line. The other part is actually the input preparation. So the part concerning the temperature and humidity sensor reading, the quantization, the copy of the data in the input tensor, and after that, the invocation of the model. Once you have invoked the model, you can read the data, dequantize, and definitely say, well, yes, it knows, or no, it doesn't, accordingly with the output value. And that's it. So I don't want to add more than that. Of course, I'm more than happy to answer your questions, but all these details, the details about the program and the explanation about each step will be all reported in the book in a detailed way. I would say that's it.
Awesome. Thank you so much, Gianmarco, for walking us through the 6 steps in order to deploy a tiny machine learning model onto an Arduino device. Super helpful. I would definitely be excited for everyone to check out the book and try it themselves. We will be going for another 10 or 15 minutes. I would like to share with you the Newton platform and how we're able to achieve similar like results. So I will quickly share my screen here. All right, so we had just seen this particular walkthrough with Gianmarco. And so if we take a look at how we can do this project with Newton, once you've done the data acquisition step, then you can leverage Newton to automatically build a neural network that you can download and deploy. So I'm going to quickly jump directly into our platform. So for those of you who aren't familiar with the Newton platform, it is all web-based on Google Cloud. If you're interested, you can go and sign up, and we have a free version for developers. So if you would be interested in creating this solution on the Newton platform, once you've gotten the data set, you can create your new solution. Here you can see I have built quite a few different AI and ML projects. We also have various different use cases that you can explore with already preloaded data sets. So what we're going to do today is create a new solution. So this will be the TinyML Cookbook use case. Then we will click next. Once we've created the new solution, we'll then want to upload our data set. So here I have 3 data sets, the train data set, the validate data set, as well as a test data set. So I'm going to go ahead and upload the training data. And so this is all of the data that includes the target variable. And here is a quick snapshot of the data set, as well as I had mentioned, and Gianmarco kind of showcased, 0s for no snow and 1 for snow that we experienced. Once we have done that, we're going to quickly go into the advanced mode, and I will also add the validation data set that we have. And that was just saying that I had already uploaded the data set into the platform. So it's just showing a warning. The next thing that we're going to do is we are going to select the target variable. And then we will click next. Once we've done that, the Newton platform has identified that this is a binary classification problem, and that the primary metric is accuracy. However, you are able to choose any that you want. And then I will enable the TinyML. And then once I have done that, we'll turn off float, and then we just click start training. So now what this is going to do is fire up a GPU for training on Google Cloud Platform. So it will take a little bit of time. So I've already created a solution. If you'd like, sometimes training can take a couple of minutes or hours. So you can put your phone number in here and it'll text you when it's done. In this case, I've already created the solution and trained the solution. So when the training is complete, this is what it will look like. So it took 24 minutes and we were able to achieve an accuracy of 88. Within this, we've also provided various different analytics tools. So I would like to highlight a few of these that kind of showcase some of the things that Gianmarco was sharing with us. So here we can see some information about our overall data, how many rows and columns, size, and etc. And here we can also see the continuous data. So in this case, temperature distribution are related to the target variable. And so you can scroll through and take a look at the different features in relation to that target variable. Additionally, Gianmarco had mentioned creating the balanced data set. So here we can see a 50% distribution of no snow and 50% distribution of snow. We also provide some data and analytics in relation to correlation. This is kind of one of my favorite pieces of information. So we can see how the different target variables are correlated with the target variable as well as each other. And additionally, as we saw, not only does the Newton platform calculate the target metric, but we calculate all of them as well. And on the left here, you can kind of see the overall model quality based on accuracy, precision, recall, etc. Now, once the training is complete, this is the point where we want to take a look at how we can do predictions. So once the model's created, there are 3 different ways to be able to do the predictions. So all you need to do is click this button and enable predictions. In this case, I was able to, if I wanted to do a web prediction, what I would do is click start, and then I would upload my test data set. I've already done that in the past. Additionally, you can access your models via REST API. We provide some sample code in order to do that as well. And then lastly, from the TinyML perspective, in order to deploy onto the microcontroller and device, we also provide the downloadable file with different formats in order to deploy onto the microcontroller or device. One of the things that I wanted to highlight here as well, within the metrics, here we also see here at the bottom the number of coefficients, the size model on kilobyte, as well as a file size for embedding. So under 1 kilobyte, which is awesome. Additionally, we've added some pretty cool features here. It's kind of a long word, the historical model to data relevance indicator. So as we're feeding in new predictions and the data is changing, we can actually see if this number gets lower, that the model is not as relevant to the data. Additionally, we can see the feature importance matrix, which shows the different features and how they are influencing the predicted value. In the case that you're wanting to evaluate the predictions themselves, you can leverage the web tool. So once you've uploaded that data set, the Newton platform will provide you with the predictions. So everything to the right here are all of our values, and then everything to the left here is what Newton produced. So here in this particular case, we predicted a 1, and there's a probability. There is a probability of a 0, 42, and then a probability of 57. So if we'd like to look at this individual prediction and kind of see what's kind of influencing that, and what are the different changes in particular variables that might influence the predicted value. So in this case, we predicted 1 with 57% accuracy, and at this current temperature level that you see here. Now, if we were to increase the temperature to this threshold point, we would see that we actually would predict no snow with a very high level of probability. And you can do this with all of the different features. Additionally, you can set different threshold values, and the platform will show you where kind of where you would need to be in order to match that threshold as well. So yeah, in summation, overall, 3 easy clicks, and you're able to build a model. So yeah, happy to take some questions as well.
Andrew, we have a question. Is the platform of Newton AI also explained in the book? No, but we can explain it right now. I think we have some slides about the platform and how it could be useful for your projects. Maybe you can jump to this, Andrew, and answer this question and show us some slides.
I'm not familiar with the slides. Could you actually repeat the question again?
Yeah, about the Newton platform.
Yeah, what about it?
Yeah, our presentation. Mm-hmm.
Sure. Was there a particular slide that you were referring to, or?
No, the question is about the Newton platform. Maybe you can say some words about how was the features, also we had a question, was the difference and advantages comparing to 𝘬𝑃 solution, and what's TinyML model size that we get on platform. You can start from the beginning, I think.
Sure. I mean, we don't really have that much time to go through everything, but I will kind of say a couple of words. So the Newton platform is designed to be self-service. So anyone who doesn't have experience with data science or machine learning can be able to leverage machine learning and embed them into their microcontrollers. Some of the differences that we have seen is that not only is the workflow automated, but because of the unique and patented framework, we're able to build models in one iteration. In addition, we don't have the need for compression. So some of the things like we saw, like quantization or pruning, we don't do. As you kind of saw, it's fairly easy to use, 3 clicks, no code SaaS solution, and you can upload your data, train your model, and get the model from there. Also, not just finding the best metric can always be advantageous. There's lots of different ways to leverage machine learning, like neural architecture search, other AutoML tools, or TensorFlow-like, Keras, etc. What we do is we will optimize the model in that one iteration at a minimal size, because we're actually building the model from the ground up, neuron by neuron, rather than taking a fully connected network and then doing some of those compression techniques. So in some of the cases, we've been able to see models up to 1,000 times smaller than some of the other frameworks or products. And also we see few coefficients in neurons, very small in size, as I kind of mentioned as well. here are a few benchmarks between some different use cases, and on the right side, you can kind of see the advantage as well. We also support 8, 16, and 32-bit, where in some cases other products don't. Additionally, like I mentioned, free of use for developers, other than the infrastructure cost for training the models. And here's a link to get started. And it's just shown the model in action and kind of how we do it as well. So yeah, we'd be excited for all of you to try out the platform and get started. And just a small comparison that we saw in the snow prediction with accuracy and size comparison. As I had showed on the platform, there's some different use cases there. So please feel free to go and explore. Additionally, check us out on Ḥackster.io. There's different developers who've created solutions, and there's step-by-step on how to implement those use cases. So yeah, hopefully that answered the questions.
Yeah, thank you, Andrew. By the way, on the Ḥackster, we also upload the weather station case that Gianmarco presented today. It's an alternative solution by using Newton platform, and you can also check it, as well as other amazing use cases and AI projects that can inspire you to develop your AI solution. Now let's check also. Yeah, thank you. Let's check also the Q&A. I think we missed a couple of questions there. Andrew, can you?
I can address those. So how can we separate the data set in train, test, and validation for the Newton Cloud version? So in this case, we wanted to replicate Gianmarco's use case. So we use the same method there, but there are different methods for splitting your data. And we'd be happy to help you out if when you join our Slack, if you have any questions about splitting data. And then there's another question: if the Newton platform, if we don't select TinyML, it creates a general classical ML model. Actually, no, that's not the case. So the Newton platform in its completely automated, non-ML mode, will actually still build really small models because of the framework in which we build the models. So we don't use any non-neural architecture like XGBoost or anything like that. It's all internally developed, but great questions.
So there was an interesting question in the QA about what type of real-time classifications we can do on microcontrollers. So this is a difficult question because, as I mentioned at the beginning of this presentation, machine learning and the target platform, they need to know each other at best. So although maybe there are some use cases that cannot run in real time, for instance, keyword spotting is a good use case, but in some cases it's not cannot go in real time. This doesn't mean that it doesn't work, because if we implement the right model, we can make it working. I can give you a very simple example. In the book, I use a virtual platform, which is an ARM Cortex-M3, which is very old, 8 years old. 8 years ago, we couldn't run image classification. But now, thanks to the evolution of machine learning, we can run image classification, and I'm talking about CIFAR-10. The platform didn't change, but the model, yes. So I'm pretty sure that if there are no possibilities to run in real time some use cases, well, if we tweak the model and we have smart solutions, there is definitely the way to make it running in real time.
Perfect. Awesome. Thank you for that.
Yes, great. We see now a very high speed of technology development, and especially in TinyML. And thank you, Gianmarco, also to share with us these industry trends. Okay, so let's check if we have some more questions. Meanwhile, you type your questions in the chat. I just would like to repeat the same information that I shared with you. We have a Slack channel where you can join our community, AI Global Community, where you can find a lot of information that we share, also records, and from today's webinar, we will upload our records on YouTube, on our Slack channel. If you have some more additional questions, if you want to repeat and practice on this use case, just go for it. And if you have some questions on any support, you can connect us, our technical team, our data scientists, and we will be very helpful, very happy to help you in this journey. Thank you, Joseph. Joseph, Joseph, thank you so much. I hope you, Joseph is from Boston University. Thank you so much for organizing this webinar for us and for this opportunity to give this masterclass to Boston University students and to community members. Yeah, thank you, Juan Antonio. Thank you. So again, you are very welcome to join our Slack. You are very welcome to join our LinkedIn where we will be publishing announcement about new events, new webinars, new very useful masterclasses. We had some questions, Gianmarco, about how people can get your book. We shared some links, but I think maybe we can think about some special discounts for our dearest attendees of today's webinar. What do you think? Please think about it.
Yeah, I mean, we need to talk to Pact for sure first.
Yes.
But definitely we can think about. What I can suggest is also to add me on LinkedIn. This is the only social media I use at the moment, a bit Twitter, but mainly LinkedIn at the moment, where I'm posting the other events where maybe I'm gonna have a giveaway session at the end. But definitely we can talk offline, so we can check with Pact as well, William.
Yeah, great. And of course, you are very welcome, everyone, to check out Newton platform and to explore the automated design of the TinyML solution with the help of Newton. And we have a lot of, like a guidance and, as Andrew mentioned, on the platform, some preloaded, pre-trained data sets that you can use and play with in order to train and understand the whole pipeline. You are very welcome. So yes, please join us in next session. And I would like to say again, thank you so much, Gianmarco, to be with us today, to give so deep diving to the use case. I'm sure it was very, very, very insightful and very helpful for all.
Pleasure to see you, Gianmarco.
Yeah. Thank you.
Yeah, I mean, it was my pleasure, honestly. Thanks to you for organizing this event, Boston University as well. But for me, it was absolutely a pleasure, really. Thanks a lot.
Awesome.
Okay, we see each other on the next masterclass.
Yep.
You enjoyed. Thank you so much, everyone. Bye-bye.
Thank you, everyone. Bye-bye.